too long class that we're going through tonight, but I don't think the notes itself are super long. And so hopefully it'll be kind of a nice, easy transition as we go into Thanksgiving break. So just as a reminder, even though I'm sure you're all aware of this, tonight is our last class for a whole week. So next week, the entire week is Thanksgiving break for you guys and for us teachers, which is nice. And so you have the whole week off, no daily assignments, no Google Meet classes, no anything happening next week. So that's the week of the 23rd to the 27th. Yeah, Victoria, do you have a question? Yes, no?
No.
Okay. No worries. So our next class meeting is actually, I don't mean to shock anybody, but it isn't going to be until December. That's right, December 1st will be the next time that we meet together as a class after today. So enjoy your Thanksgiving week off. You guys have definitely earned it and deserved it after all of the craziness of school and work and doing online stuff all this time over the course of the week. And so today we're going to cover our final topic after or relating to the atoms and molecules and stuff that we've been talking about so far. Sorry, I'm helping somebody try and get into the class. Okay. All right, hopefully that works for them. So the last thing that we're going to talk about with these atoms and molecules that we've been going on about is how is it that these atoms actually stick together, fuse together down at like the chemical level. So last week Tuesday, we were talking about our compounds and how we have these compounds of these different atoms that are fused together, stuck together chemically. Today, we're going to talk about how do they actually do that? How is it that these atoms get chemically combined with each other? So let me go ahead and pull up the notes. Wait, this one is the one that we want. All right. So just as a reminder, your midterm exam is still up, still going on. Again, it's not due until the end of the night on Friday. So you have the rest of the night tonight after this class is over and all day on Friday to finish working on the midterm and turn it in. Again, it covers all the stuff that we've talked about in class so far, including the mixtures and compound stuff that we talked about yesterday. If you have any questions about it, feel free to reach out to me. Obviously, I can't directly help you answer a question, but if you're just confused about what a question is asking, or you need some clarification on what type of answer that you should be giving, that is stuff that I can do my best to help you guys out with. So a couple people have actually already turned in and completed the midterm, which is awesome. If you haven't yet, no worries, no big deal. You have until the end of the day on Friday to get it turned in. So that is what I wanted to mention regarding the midterm there. So today we're going to talk about chemical bonds, which is how these different little particles, these different atoms that are floating around, get stuck together. And so when I talk about bonds, we're not talking about this bond. We're not talking about this bond either, even though he is definitely a great bond. But that's not what we're talking about. We're talking about chemical bonds, the ways that atoms get fused together, get stuck together down at the chemical level. So we've talked a lot about atoms over the last 2 weeks or so. All right, and just as a refresher from last week when we were talking about the protons and neutrons and electrons and all sorts of fun stuff like that, atoms are the smallest units of matter, the smallest building blocks that go into making up the rest of the universe. And they're comprised of 3 different major particles. In this case, we have our little helium atom. And so atoms are made up of positive protons. So that's what these purple circles here are with the little plus signs in them. Our protons are positive, and they like to hang out in the nucleus and kind of this middle section down here. Our neutrons are also in the middle. They are neutral, so they don't have a positive or a negative charge. They're neutral neutrons. They also like to hang out with the protons in the nucleus down here. And then we also have our electrons out around the atom. Electrons have a negative charge, and they don't hang out in the middle of our atom right here. They like to hang out around the outside of the atom. So the electrons are what we're really going to be focusing on today, because even though the protons and the neutrons are important for the atom, it's our electrons that are responsible for doing a lot of this bonding activity. So the other major thing that we talked about last week was our electron shells, right? That idea that surrounding our atoms are different kind of layers of electrons or different shells of electrons. And each cell was able to have a certain number of electrons on it, right? So our total number of electrons we could figure out because it's equal to the number of protons, which is the same thing as our atomic number. So all of our electrons go in a particular order on these electron shells that kind of circle the outside of the atom. So they don't go into the middle in the nucleus, they circle around in these shells around the outside of the atom. So how many electrons we have on our electron shells can determine how that atom is going to react with other atoms that it might come into contact with. So before we look at the electrons going around their shells. I wanted to do a kind of a quick review with you guys. So when we talked about the electron shells, we talked about there's the first shell, the kind of most inside shell, and then there's the second shell, the kind of middle level shell, and then if we need it, there's a third shell, kind of the most outside shell. So who remembers how many electrons fit on the first shell, on that inside shell? How many total can we fit in there? Yeah, Annette, go for it.
2.
2, precisely. So 2 electrons fit on our first inside shell. What about our second shell? How many electrons fit on the second electron shell? Yeah, Veronica.
8.
8, bingo. 8 go on that second shell, 2 go on the first shell. And then what about our third shell, our outermost electron shell that we talked about? How many electrons fit on that shell? So our first shell has 2. Our second shell can fit 8. How many can fit on our third shell?
Doesn't it depend on how many are on the second? Like it's still 8, but however many are left over?
It possibly, yeah. I'm just talking about what's the maximum number that you can fit on the third shell. Yeah, Annette, do you remember?
18.
Not 18. Nope. If you have a full third shell, that means you have 18 total electrons. But how many can fit on the third shell by itself?
Oh, 8.
8.
Yeah, 8.
Yeah.
Exactly. So 8 electrons total can potentially fit on the third shell. 8 electrons can potentially fit on the second shell, and 2 electrons can fit at most on the first shell. Like Veronica was saying earlier, sometimes you don't need to go all the way up to the third shell. It might depend on how many electrons that you have in your atom, but that's the maximum amount that will fit. So once you get 8 on that third shell, it's full. You can't fit no more electrons up there. So bingo. First electron shell can fit up to 2 electrons. And each shell after that, so the second one and the third one, can hold up to 8. So a new term that I'm going to throw at you guys here are called valence electrons. So valence electrons are the electrons that are on the outermost shell of the atom, whatever shell that is. If you're a really small atom and you only have 1 or 2 electrons, then your first shell is your outermost shell, right? You don't have any more after that. Or if you're a slightly bigger atom, then maybe you have a couple of electrons on the second shell. That would be your outermost shell in that case. Or if you're a little bit larger atom and you have electrons on the first, second, and third shell, then the electrons on your third shell would be your valence electrons. So whichever shell is your outermost shell, your first, second, or third, the electrons on that shell are called your valence electrons. So like you guys had oxygen for your homework the other day that had to do with the electron shells. And oxygen has 8 electrons, which means that 2 go on the first shell and 6 go on the second shell. Those 6 on the second shell would be the valence electrons of oxygen. So oxygen has 6 valence electrons because that is how many electrons are on the outermost shell of oxygen, which in oxygen's case is its second shell. So for some more examples, hydrogen, the very first atom on the periodic table, it only has 1 electron. So it has 1 valence electron and 1 electron on its first shell. So hydrogen's all about the number 1 down here. We make a little bit bigger, we go up to carbon. Carbon has an atomic number of 6, so it's got 6 electrons. We can fill up the first shell of carbon, and then we have 4 remaining electrons left over. So carbon has 4 valence electrons. So on our little diagrams here, the filled in dots are the electrons that are on that shell. And then the sort of empty circles or the empty dots are the remaining spaces on the shell where there could fit more electrons if we had any. So for example, carbon has 4 electrons on its second shell, but the second shell could potentially fit 8 electrons. So there's 4 filled in electrons and then 4 empty spaces on carbon shell. Same thing with nitrogen. Nitrogen has 7 electrons. So 2 on the first shell and then 5 valence electrons on the second shell. So there's 3 spots left over in nitrogen. And then like I was just saying, oxygen has an atomic number of 8. So we've got 2 on the first shell, 6 valence electrons on the second shell, with 2 spots left over. So the reason why I am pointing out the spots remaining is this has to do with something that's going to be important for making the chemical bonds that we're going to talk about in a little bit. And that is the idea of the octet rule. So the octet rule says that when you have a shell like the second or third shell that can fit 8 electrons on it, atoms tend to either gain electrons or lose electrons or share electrons so that they could have 8 electrons on their outer shell. So the atoms are sort of the most stable. They are the most happy when they have a full outer shell. So carbon, nitrogen, and oxygen all wish that they had a completely full second shell of atoms, or electrons, excuse me. But they don't. They're very sad. They have some spaces missing on that second shell. So the octet rule says that these atoms are going to want to trade electrons or lose electrons or gain electrons by reacting with other atoms so that they can get 8 electrons onto their outer shell. So, for example, carbon has 4 electrons on its outer shell. It has 4 valence electrons. So carbon would like to gain 4 more electrons. It would like to fill in these empty spaces with electrons that it gets from other atoms so that it can get up to that full second shell. 4 empty spaces means it wants to gain 4 more electrons. So, in a similar vein, what does the octet rule say about nitrogen? How many electrons would nitrogen have to get in order to have a full second shell?
3.
3, exactly. Nitrogen has 5 valence electrons, which means it has 3 empty spots for new electrons to be added so that it can get up to that 8 outer shell number that it wants to get to. What about oxygen? How many more electrons would oxygen want to gain in order to fulfill the octet rule?
Two?
Yes, exactly, 2. So oxygen has 6 valence electrons. It's got 6 electrons on shell number 2 right here. So oxygen has 2 more. It has essentially 6 out of 8 electrons. So the octet rule says oxygen would like to gain 2 more electrons in order to get to that 8 outer shell number. So valence electrons are how many electrons are on the outer shell. And then the octet rule says that atoms want to try to have 8 electrons on their outer shell in order to be the most stable. So however many they have to add on or let go of in order to get to 8, they're trying to make their outer shell be a nice full round 8 electrons.
Hi, Mr. Stanley.
Hey, Cameron.
I'm
Good to
sorry
see
I'm
you.
late.
That's
Good to
fine.
see
No
you.
worries. Thanks for being here. Thanks for making the effort to
Thanks
join
for
up.
allowing me to come.
Yeah, of course. Welcome, welcome. All right. So valence electrons on the outside ring, and the octet rule says we're trying to make that outside ring be 8. That's kind of what octet means. It's like 8. So here are some more kind of pictures of electrons and their atoms. So here's the 3 that we were just looking at: carbon, nitrogen, and oxygen. We could go up to higher electron numbers, like fluorine has 7 electrons on its outer ring, or down lower, like boron has 3, and beryllium has 2, and lithium only's got 1 little electron on its outermost ring. So 2 things to notice in our little periodic table diagram here. The first one is that when you go down a column, you have the same number of electrons, of valence electrons, on that outside shell. So lithium has 3 electrons, so it has 1 electron, 1 valence electron on its second shell. Sodium has 11 electrons, but it also has 1 electron, 1 valence electron on its outer shell. Armisha, I don't think you guys are ever going to have to draw out the electron shells in this class. If you ever do, or if you ever want to, you don't have to draw them exactly like this. However best lets you kind of see the electrons going around on their shells works for you. You don't have to exactly group them up in the way they're grouped up on here. Good question, though. So 1 valence electron, 1 valence electron. Same thing for our second column over here. Beryllium, 2 valence electrons. Magnesium, also 2 valence electrons. Boron and aluminum have 3. Carbon and silicon have 4. Nitrogen and phosphorus have 5. Oxygen and sulfur have 6 valence electrons. Fluorine and chlorine have 7 valence electrons. And then the second big thing that I wanted you guys to notice is something that I talked about a little bit in a previous week. But our final column over here has completely full outer shells. So helium has 2 electrons on its first shell. Neon has 8 electrons on its second shell. And argon has 8 electrons on its third shell. So for these guys, the octet rule would say that they want to gain or lose 0 electrons, right? These guys are happy. They've got full outer electron shells. They don't need to be adding any electrons or getting rid of any electrons in order to have a full shell. So these guys don't really like to interact with the other atoms out here. They're already got their full 8 electron shells, so they are sitting fat and happy, essentially. You can also sometimes show the valence electrons with what are called electron dot structures. I just wanted to show these to you guys because they may come up once or twice in a future section of the notes. So I just wanted to show it to you kind of now so you didn't get too confused. So this one just shows the valence electrons, the outer shell electrons, with these little dots around the symbol for the atom. So like we were saying earlier, lithium and sodium both only have 1 electron. Beryllium and magnesium have 2. Carbon and silicon both have 4. So you have kind of 1, 2, 3, 4 on either side. Nitrogen and phosphorus have 5. And then over here, neon and argon have a full set of 8. So if you see a picture like this where it's the symbol for an atom surrounded by a whole bunch of dots, those dots are just indicating the valence electrons. All right. Anybody have any questions so far on electron shells, valence electrons, or the octet rule?
No, Mr. Stanley.
All right, got it. Thanks, Carmen. Okay, so moving on from that, the reason why I wanted to kind of start off these notes by talking about these electrons, and especially these valence electrons, is because they are extremely important in the process of making chemical bonds. So the octet rule is that thing saying that atoms are trying to fill up that outside ring with 8 electrons. The way that they can fill up that outer ring is by chemically bonding with other atoms that are around them. So there's 3 major types of bonds that we're going to go into detail about today. The 2 most important ones are these first 2, ionic bonds and covalent bonds. So those are kind of the big 2 that we're really going to dive into. Metallic bonds are also around. We're going to kind of talk about them much more briefly. They're not quite as important as these 2, ionic bonds and covalent bonds. So ionic bonds are when we transfer an electron from one atom to another atom. Essentially, we give away an electron between atoms. And covalent bonds are when atoms share electrons with each other. Again, all because we're trying to fill those outer electron shells and satisfy the octet rule. We're trying to make it to that magical 8 number. So the first one that we're going to talk about is ionic bond. So the characteristic of an ionic bond is that it is formed between 2 ions, or which is another name for types of atoms, by the transfer of electrons, meaning one atom gives away its electron and the other atom receives it. So the electron kind of gets passed from one atom to another. This is what makes an ionic bond. So how does an ionic bond work? What exactly is going on when we're giving away or taking in our electrons? So ionic bonds usually happen between metals and nonmetals. Just generally, those are the two that kind of come together to make these ionic bonds. Again, it's formed by transferring our electrons, passing an electron from one atom to another atom. Blah, blah, blah. Don't really worry about those last couple. Well, I guess this last one is a good example of this first point. So, for example, one that we'll talk about a lot here in just a second, sodium chloride. Sodium is a metal and chlorine is a nonmetal, so they like to bond together. Calcium is another metal, and again, chlorine is a nonmetal, so they like bond together. Potassium is a metal, and oxygen is a nonmetal. And so the thing that all these guys have in common, besides the fact that one of them is a metal and one of them is a nonmetal, is that they're all bonded together. They're all compounds. So again, this ties back into what we were talking about yesterday about how when we have two or more different atoms bonded together, whether it's one sodium and one chlorine, one calcium and two chlorines, two potassiums and one oxygen, these are different atoms that are bonded together, and that makes them a compound. So the best way to kind of think about ionic bonds, at least in terms for me, is by visualizing it. And I apologize in advance. I can't stop this animation and like pause it and talk about it. So we're just going to kind of talk about it on the fly right here. So we talked about sodium and chlorine are two different atoms that make very strong ionic bonds together. So you see sodium over here is the atom symbol is Na. And sodium's got this little yellow electron. So the yellow guy goes with sodium. And if you remember from the diagram we were looking at earlier, let me zoom back to that real quick. Sodium has one valence electron. It's got one lone electron hanging out there on its third shell. So for sodium, the octet rule says that it's actually easier for sodium to lose an electron in order to get to that 8 outermost shell. Because if sodium loses its outside electron, then it doesn't have a third shell anymore, but it already has a full second shell. So if sodium can trade away this one electron and have a full set of 8 electrons on its second shell, then it will fit the octet rule. On the flip side, chlorine over here, its buddy that it's about to bond with, has 1, 2, 3, 4, 5, 6, 7 valence electrons. So if chlorine can get one more electron to hop on to its third shell, then it will satisfy the octet rule and have a nice third shell of 8. So hopefully you could already see why sodium and chlorine fit so well together. Sodium wants to lose an electron to have a full second shell, and chlorine wants to gain 1 electron in order to fill in the one missing spot on its third shell. So an ionic bond is exactly how they do this. So sodium has the 1 little yellow electron. Chlorine has the 7 red electrons that are surrounding it. So when they make an ionic bond, sodium gives its 1 electron to chlorine. Now, sodium has an empty third shell, but a full second shell, so he's happy. Chlorine has 1 more electron, gives it a full outer third shell, so chlorine is happy. So when sodium gives its 1 electron to chlorine, they don't just hand off and then split apart, right? This is a chemical bond. They're trying to stick together. So when sodium passes off that electron to chlorine, it causes them to stick together. So here's another kind of fun animation that I found kind of showing what's going on. So sodium and chlorine, in this case, are these 2 different dogs that both have a bone. But when they come into contact, chlorine takes the bone, takes the atom from sodium, which causes them both to kind of stick together with each other. So one atom takes all the electrons and the other one gives them up. So sodium takes its 1 electron and gives it to chlorine. Now, if you're wondering, well, after it passes the electron by, why don't they just float off? Why can't they just have nice, happy, full outer shells and then leave and go their separate way? Why do they get stuck and bonded together? The reason has to do with their new charges. So you may have noticed on that animation from earlier, when sodium gives away its electron, it becomes a little bit more positive. And when chlorine accepts that electron, it becomes a little bit more negative. That's what we're seeing here. Sodium is positive, chlorine is negative. The reason why we have this change in the charge has to do with that 1 little electron that got moved. So, does anybody remember what the charge of an electron is? Is an electron positive, neutral, or negative charge?
Isn't it neutral?
Not quite. The neutron is neutral.
Yeah. So it's negative?
Yes, exactly.
The proton's positive?
Precisely, Breeze. Protons are positive and electrons are negative. So this little electron that got just hopped over from sodium to chlorine is negatively charged, which means that when chlorine takes this electron, chlorine becomes a little bit more negative, right? If you remember when we talked about how to calculate your number of protons and electrons, we said that in a normal neutral atom, the proton number and the neutron number, or the proton number and the electron number equal each other, right? Same number of protons as electrons. So that's chlorine over here. Chlorine has 17 protons and 17 electrons. When that extra electron gets added, chlorine now has 18 electrons, but it's still got 17 protons. So now what's happening is the negative charges are outweighing the positive charges and making chlorine a little bit more negative than it was earlier. So now, by getting that electron, chlorine has become more negative. Sodium has the opposite thing happen. Sodium has, at the beginning, 11 protons and 11 electrons. But when it loses that electron, now sodium still has 11 protons, but it only has 10 electrons. So sodium becomes a little bit more positive when it gives its electron away. So we get the transfer that happens. Chlorine gets the electron and becomes more negative. Sodium gives away the electron and becomes more positive. And the thing about charged particles is that they are attracted to their opposite. So if you ever heard the phrase like opposites attract, like if you know somebody who's in a relationship and the two people seem like completely different people, but somehow they get along great and are in a relationship with each other, and people are like, oh, well, you know what they say, opposites attract. Sometimes that works out for relationships, sometimes maybe not. But in chemistry, it always is the case. So positive charges and negative charges are attracted to each other. They want to be close to each other. So when sodium becomes a little bit more positive and chlorine becomes a little bit more negative, that causes them to be attracted and essentially stuck to one another. All right, it's almost like if you've ever played with magnets before and one side of the magnet doesn't really go together, but then when you flip one around and they get stuck together, the same thing or a similar kind of idea is going on right here. So the positive sodium and the negative chlorine are going to stick up together and form the compound sodium chloride. So it's an ionic bond because we transfer an electron from the sodium to the chlorine. So the sodium gives away the electron, the chlorine takes the electron. Afterwards, the two particles then get ionically bonded together due to that positive and negative that attract. So that's how we're able to form compounds through ionic bonds. We give away some electrons and then the atoms become attracted and stuck to one another. So you may remember that I mentioned in a previous slide from the other week that when we put sodium and chloride together, we get table salt. So sodium chloride is table salt, and it forms these nice big kind of crystalline structures when you get a whole bunch of them all ionically bonded together. And that's what gives salt that kind of crunchy, flaky feeling. Any questions so far on ionic bonding, transferring electrons, positive and negative charges? Any questions about our ionic bond process? All righty. If not, then we can move right along to our next bond, which is a little less confusing, a little more straightforward, which are covalent bonds. So in a covalent bond, we're no longer transferring and giving away electrons. Instead, we're sharing electrons. So both atoms are holding on to a shared set of electrons. So when we give away and take electrons, we have an ionic bond. If we are sharing electrons, we have a covalent bond. So covalent bonds tend to be between nonmetals, especially things like oxygen, carbon dioxide, water, butane. These are all covalently bonded atoms. And they bond by sharing pairs of electrons. So again, they're not giving away and taking, they are sharing. Again, don't really worry about that third point down there. We're not really talking about conductivity. But covalent is all about sharing. So, the way that covalent bonding works looks a little bit like this. So carbon, if you remember, has 4 valence shell electrons, right? Carbon has atomic number 6, which means that it has 2 first shell and 4 second shell electrons. So carbon's electrons are indicated in blue here, right? So carbon has 4 electrons on its outer shell. Hydrogen, our super simple basic atom, has 1 electron on its outer shell. So carbon would like to have 8 electrons on its outer shell. Hydrogen, he's so small, he wants 2 electrons on his outer shell, because his outer shell is the first shell. So the way that they can both get what they want without taking away or giving away electrons is that the carbons and the hydrogens share their electrons with each other. So carbon is able to bond with 4 hydrogen atoms at the same time, because in each one of our bonds, we use 1 of carbon's electrons and 1 of hydrogen's electrons. In this case, hydrogen's only electron. So on this bond, hydrogen has contributed 1 electron and carbon has contributed 1 electron. Same thing up here. We have carbon electron number 2 being shared with a hydrogen electron. Over here, we have carbon electron number 3 being shared with a hydrogen electron. And down here, we have carbon electron number 4 being shared with the hydrogen electron. So carbon gets to feel like it has 8 electrons on its valence shell. And each one of these 4 hydrogens gets to feel like it has 2 electrons on its little first valence shell. So this is what covalent bonding is all about. Sharing your electrons so that both atoms are able to feel like they have that full outer shell. So if we have some electrons that have, in this case, we have 2 electrons. Both of them have 7 valence shell electrons. So when these guys bond together, they're not giving away and taking electrons, because that would, well, one atom would take and get 8 electrons. If the other atom gives 1 away, it only has 6 electrons, which isn't that 8 number that it's looking for. So instead, they don't do that. They each share 1 valence shell electron. And so on our first atom, when it has that 1 shared with it, it feels like it's got 8 electrons. The other atom has its own 7, and then the 1 that's being shared from the first atom, so it also feels like it's got 8 electrons. So by sharing the electrons together, each atom is able to fulfill that octet rule. Each atom is able to get 8 electrons on its outer shell, even if one of those 8 electrons is shared and is coming from another atom. So this is the main difference between ionic bonding and covalent bonding. In covalent bonding, we're sharing electrons in order to make sure each atom gets that 8 electron outer shell. Like I said, that one a little bit more straightforward. So the bond is because now when these atoms are sharing their electrons, they're physically stuck together. So their outer shells essentially overlap with each other a little bit, and they become bonded together through this sharing of electrons. So as soon as that electron sharing happens, then they are physically stuck together due to those combined electrons. It's a little bit different from the ionic bond, where they get stuck together due to the positives and the negatives being attracted to each other. That's what's happening in the ionic bond. In the covalent bond, we don't have positives and negatives. We just have the pairs of electrons that physically connect the two atoms with each other. Both types of bonding result in compounds of different atoms being connected to one another. They just go about it in a little bit different ways. Anybody have any questions about covalent bonding? Any questions about how this electron sharing happens? All righty. So the last type of bonding, we're just going to kind of breeze through really quick. It's not going to be on any homework questions or on any test questions. So I'm not worried too much about it. The last type of bond is called a metallic bond. And it's called that because it's mostly found when multiple metals become bonded together. So you may remember I mentioned that in ionic bonds, we tend to have metals and nonmetals. Covalent bonds tend to be 2 nonmetals, and metallic bonds tend to be 2 or more metals. So essentially what happens in a metallic bond is it forms sort of this electron cloud around the atoms, where the metals are able to kind of line up and share their atoms in such a way that there's sort of like a flow of, I like this picture a little bit better. There's sort of like a flow of electrons all around all of the atoms that are there. And so all of the metal atoms are able to kind of fulfill that octet rule just due to the sheer amount of electrons that are kind of floating around and crisscrossing around all the different atoms that are present. All right. So again, that's metallic bonding. I just wanted to bring it up because it is a third type of bonding. But I would say it's not quite as crucial to know about as those first two, those covalent bonds and those ionic bonds. Anybody else have any other kind of final questions about valence electrons, electron shells, ionic bonds, covalent bonds, anything that we've talked about so far tonight? Anybody have any questions?
No.
All right, thank you, Cameron. Anybody else, any final questions about the notes that we just went over? All right, thanks, Veronica. All right, so for the assignment that got posted today, since you guys are still working on, where'd my mouse go? There it is. since you guys are still working on your midterm, I want to make it a pretty simple one. And so the assignment is on chemical bonding, and it just shows a couple basic examples of pictures of chemical bonds. And I want you to tell me what type of chemical bond it is and how can you tell. So in both pictures, we have two different atoms, lithium and fluorine. And so we have this first diagram right here. And then the questions of what type of bonding is pictured and how can you tell? What tells you that it's a covalent or an ionic bond? And then same thing with the next picture. We have a hydrogen and we have a fluorine. And they get bonded together. And I want you to tell me what type of bonding is pictured and how can you tell? And that's it. 2 different pictures, 4 questions asking about what type of bond is present and how can you tell that that is the bond that is there. So hopefully it should be pretty straightforward and easy to do so that you don't have to worry too much about it and you can really focus in on that midterm. Again, the midterm is up right now. It's going on. You can go in and look at it and check on it anytime. It is not due today. It is due by the end of the day tomorrow. So if you haven't worked on it yet, if you haven't finished it yet, don't worry. You still have the rest of the evening tonight and all day tomorrow to work on it and turn it in.